prefer B.
I think this is fine. Okay, so you guys have any questions
Yeah, I was supposed to ask you.
in particular? Yes, Michael?
I have a question, but it's probably better to ask it later.
Oh.
I want you to do an example of the spectral decomposition problem.
Uh-huh. Okay. Very good question. I think later is a good idea. What was your question?
I was going to say, can you do a Jordan form problem?
A Jordan form problem. I see. Do you guys have any questions about the start of the course?
How do you do
One to one and on to really quick.
We look through the test really quick.
I just don't remember the first part of the exam.
I forgot to bring it with me.
Sure. So, let's see. Problem one, we had to find a solution set for a system of equations, right? So basically, that's just the null space calculation that you guys have been doing a lot lately, right? In retrospect. You know, if you wanted to think about this in the kind of, if you want to think about problem one in a somewhat unconventional way, you could think A equals to, and here's a fun thing to think about. You think A equals 1, 1, 1, minus 1, 1, 0, 2, 1. Gee, I don't know. 2, 1, 3, 0, 3, 2, 4, minus 1. If you were to find the eigenvalues of this, you'd find lambda equals to 0 at least twice. I think just twice. And you would find that the basis was the span of what? Minus 2, 1, 1, 0, minus 1, 2, 0, 1. How do I know that? Without any further calculation, just looking at problem 1, test 1, like. So if I wanted to look at this as part of a larger system, that's what I did. The first two rows in that are exactly these equations, right? And then the second two rows, what I did was I just added. See what I did? I added the first and the second row to get the third. And I added the first and the third to get the fourth. So I know there are no new equations in equations 2 and 3. So basically the solution set to AX equal to 0 is the same as the solution set to the original problem that I gave you in problem 1 of the first test. So I already know what the null space is of this matrix, and consequently I know what, if the null space is not trivial, what does that mean? That means that you have vectors such that AX equals to 0 without X being 0, that means X is an eigenvector with eigenvalue 0. So, I don't know, just kind of a fun, weird way to look back at the first problem, right? Would I want to attempt a spectral decomposition for A? Why or why not?
It's not symmetric.
Yeah, it's not symmetric, right? So, being that it's not symmetric, we don't know that there exists an orthonormal eigenbasis, and so the spectral thing breaks down. Yep.
But you could form a Jordan decomposition.
You could find the Jordan form. Oh, yeah, that.
You can do it with an isomer. You know you're
Oh, but that's actually not too hard because we know that A is row equivalent to the one that I started with. Man, these markers are awful. I need to go get
Do you want
more
mine?
markers.
Mine's really nice. Serious question.
I have good ones here, Chris. I just have to use the ones. So if you look at the determinant of A minus lambda I, you get what? You get determinant of 1 minus lambda, 1, 1 minus lambda, and then the determinant of minus lambda minus lambda. Now, you see what I did? I mean, I didn't write it out, but when you subtract lambda from A, you have block diagonals. You can look at that. You've got this block, you've got that block. You have zeros down there when you subtract off lambda I. So I can actually calculate the characteristic polynomial for this one without a lot of extra work. In fact, I already know the eigenbasis for the zeros from your solution to problem 1 of test 1. And the other eigenvalues are what? Let's see here. Lambda minus 1
This is for Jordan form, right?
times lambda. Yeah, I'm trying to figure out the Jordan form. Minus 1 times lambda squared. That's my characteristic polynomial. Keep lambda. Let's see here. I don't know. Is this anything? So you get lambda squared minus lambda minus 1. Let's see here. So if I do what? That's
It's like 1 plus square root of minus 5 over 2.
yeah. It's lambda minus a half squared. If I if I added a fourth, that's to take away a fourth. So what I have is minus 5/4, right? And there's still the lambda squared. Excuse me. So after a bit, I get lambda squared times lambda minus a half minus the square root of 5 over 2 times lambda minus a half plus the square root of 5 over 2. So in fact, this matrix is diagonalizable. And so what we learned then from this, oh, I'm sorry, this was, let me call this thing A tilde, since I defined A differently at the start of this discussion. So we have that A tilde is equal to, well, rather P inverse AP will be the Jordan form for this. It's just a diagonal matrix in this case. If I put the zeros first, I'd have 0, 0, and then I've got, 1/2 plus the square root of 5 over 2, and then 1/2 minus the square root of 5 over 2. And I know that I have a two-dimensional, and everything else 0. That would be the Jordan form in this case. It's kind of just diagonal. So.
How did you know it was diagonalizable? How did you, at one point you're like, oh, well now we know that it's diagonalizable. What told you that?
Oh, okay, so for each distinct eigenvalue, you get at least one eigenvector. So once I find that 1/2 plus or minus the square root of 5 over 2 are eigenvalues, I know I've got two eigenvectors for now. But I also already know from the solution to problem 1 of test 1 that there are two eigenvalues with eigenvalue 0. Eigenvectors with eigenvalue 0, rather. So I already know the geometric multiplicity of the 0 eigenspace is 2. So 2 plus 2 is 4. That's all I need. Once I have 4 eigenvectors for a 4x4, that shows it's diagonalizable if I have 4 linearly independent
So
eigenvectors.
zeros are sufficient to count?
Well, the vectors aren't 0, right? It's
The 0 eigenvalues?
right. So these guys right here are eigenvectors with eigenvalue 0. You can take this vector and multiply that and see you get 0, right? For example. Yes, Landon?
And E1 is essentially the null space, correct? Or is that really bad?
Yes, in this case, right, E1 is the null space because it's the eigenvalue 0. So more generally, E sub j is the null space of A minus lambda sub j times I. Yes, sure.
I'm sorry. For A tilde, it doesn't have anything to do with A. You didn't do reduced, right?
No, I actually built A from A tilde, so they're the same. I mean, they're actually the same. Well, they might have different eigenspaces. I'm not sure about that, but they have the same 0 eigenspace because the equation let's say ax equals to 0 is equivalent to A tilde x equals to 0. And how do you measure equivalence of two equations? I mean, what do we mean two linear systems are equivalent? What does that mean? They have the same
solution set.
Right, same solution set. And these have the same solution set because the way I got from A to A tilde was I added the first two equations of A, to get from A tilde to A, I added the first two equations, let's say, the first two rows to get the third one, and then I added the first and the third to get the fourth. So all I'm doing is using equations that were already in A tilde to get A. So that's why I know they have the same 0 eigenspace. I would expect they don't have the same, the other things, these guys, I wouldn't expect are the same. Yes, Chris?
So you were able to just plug in the eigenvalues
directly into the Jordan form because it was diagonalizable?
Well, once I know the geometric and, once I know what the eigenvalues are, and once I know what the geometric multiplicities are, in other words, how many eigenvectors I have, then I can write down the Jordan form. Well, it's not quite that, right? I also need to know the tableau structure for more complicated examples. But yes.
I was going to say, what you would normally do, though, is you would construct an eigenbasis or a Jordan basis, right?
Oh, how to actually find the P? Yeah,
Yeah.
I would. My P, I would start with these two guys for the first thing to get my zeros, and then I'd actually have to solve to you know, P would be V1, V2, V3, V4, where this is V1, this is V2, and then V3 and V4 would be solutions like A minus 1/2 plus the square root of 5 over 2, parentheses, I. So the solution to this equation, and then,
Your eigenspace for that.
yeah, it would be a basis. Now, I know the eigenspace is one-dimensional because the algebraic multiplicity is just 1 for each one of these roots, right? So, and we know that the algebraic multiplicity is an upper bound on the geometric multiplicity. You can't have more eigenvectors linearly independent than you have a number of factors in the characters. This puts an upper bound of 1 eigenvector for that eigenvalue, and 1 eigenvector for lambda, 1/2 minus square root of 5 over 2. But those two vectors, to actually explicitly find the P, I'd have to solve those two equations, which I don't want to do.
And would that be if it wasn't diagonalizable? Or just
This
kind
is diagonalizable.
Okay.
So,
So why were you able to just ignore the P calculation and just go straight to the Jordan form?
because there are 3 eigenvalues, 0, and then 1 plus or minus the square root of 5 over 2. So that means I have at least 3 eigenvectors, because those are 3 distinct eigenvalues. However, I also know I have 2 for 0 because of the original problem 1 solution. So that's 4, and that's it. That's an eigenbasis.
All right.
And that means it's diagonalizable since you have 4.
Right. We proved that a matrix is diagonalizable if and only if, you know, there's an eigenbasis for the matrix, or the corresponding linear transformation, if you like. Yes, Lyndon?
And if you asked to give the dimension, rank, and nullity, nullity would be like 2, rank would be 2 as well, right?
For this, for which one? For
that one we have on board, or number 1.
Yeah, the rank should be 2 and the nullities 2. I can see that the rank, so rank is either the dimension of the column space or the dimension of the row space. Column space, I'd actually have to kind of think about, well, maybe not too much. They're 2-dimensional vectors, and it's clear that you're spanning the R2, which is embedded in R4. That's kind of easy to see also, but it's more obvious in row space that you've got 2 linearly independent rows, and then I just added those to build the other one, so of course row space is 2. And yes, by the rank nullity theorem, so that's actually another way you could have, independent of your calculation for problem 1 and test 1, you could have determined that the geometric multiplicity of the 0 eigenspace was 2 without even doing a calculation, right? You could look at it, you could go, aha, rank is 2, the number of columns is 4, therefore nullity is 2. Therefore, there are 2 linearly independent eigenvectors with eigenvalue 0. Without so much as a calculation, you could have by inspection seen that. It's a good question. Hey, I think I thought of a test problem. Thank you, Landon.
You're welcome.
Can you repeat everything you just said?
Explain that later.
Rather than do that, let me illustrate what I'm talking about with an example. Are there other questions while I'm erasing?
I have one.
So you guys wanted to see a spectral theorem, you wanted to see a more interesting Jordan example, and what was the other question? Yep.
Well, what do you mean by more interesting spectral example? I mean, not like, could you do one that's like find the Jordan basis for a non-nice diagonalizable matrix?
Are you asking if I can just write down a random matrix and find the Jordan form? The answer is no. I will not do that in this review session because I value your time, and that's all we do.
Could you do number 4 from our quiz by finding like the Jordan basis, since it's like, I think it's not diagonalizable.
I will consider that, but let me just, to answer Sharon's question. So if I have this, let's say I have 1, 2, 3, 4, 5, and then 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and then zeros. Or I could also play games at the final two rows, just add the first three, something like that. What's the rank of this matrix?
3.
Are you sure? I mean, if I was unlucky, like if I had the first row was all ones, then you guys would see that something else is required, right? But you're taking it on faith that there's no linear combination of the first three, right?
Yes.
That's your assumption. I think you're right. So, rank of A, which is, by the way, the dimension of the column space, or the row space, as we proved, 3. And so what we know the nullity of A plus the rank of A is equal to the number of columns, right? How many columns?
5.
5. So therefore, the nullity of A is what?
2.
2. By the way, this is also equal to the dimension of A minus 0 times I, right? So if I have lambda 1 equals to 0, then we have the geometric multiplicity is equal to what?
2.
2, but that's also equal to the dimension of E1. So the geometric multiplicity is equal to the algebraic multiplicity in this case, for the 0 eigenvalue. I guess wait a minute, do I know for sure that, I guess I'm jumping a little bit. How do I know for sure that there's not a an algebraic multiplicity of more than 2? Actually, I don't know that. I should put a little question mark on this equality. I'm not absolutely sure of that. I have to think about that more. I mean, so I have determinant of A minus lambda I is equal to, for sure, lambda squared times some g of, well, I don't want to use g, we use g for minimal usually. So say g, lambda squared times f of lambda, f of 0 equals to 0. You know, that's a question. I'm not sure if there could be another 0 that didn't produce an eigenvector with eigenvalue 0. I don't know if there is or not, without doing more calculations. But this much I can tell you, the dimension, the geometric multiplicity of the 0 eigenvalue is 2, because that's the nullity. So 0 eigenspace is kind of special, right? 0 eigenspace actually comes back into contact with the rank nullity theorem. So they're actually kind of really simple questions I can ask about it, now that you guys pointed out to me. Thank you. I hadn't thought of that before. I love these review sessions. They give me ideas. No,
It's not nice.
it's not nice.
What are they striking us? I can dealing with the board.
Now, you wanted me to look at the solution to, what was it, Landon? Number 4?
Yeah, but
Let
not
me-
like the cheating way.
Let me just try to draw together our thinking for test 1 here before I leave it. You know, remember we have problems like I give you a couple points on the graph of a polynomial. You find the polynomial. Remember those problems?
Yeah.
They still exist, and they're easy, right?
Yes.
All right, as long as I make the answers integers.
Yeah.
That's true.
I like grading integer answers though, so the odds are pretty good for that. There are problems like this, problem 3, where I don't actually give you a matrix, but you have to know how to, read the reduced row echelon form, what that means, what it tells you about the solution set. You should know about how to write a solution set as opposed to how to write a given specific solution, right? For any given, I guess for any, if you think about a subspace in Rn, you really have two choices. How can you describe a subspace in Rn?
As a generating set, span of a generating set.
Right, you can either write it as a span, or what?
Or using set builder notation.
Or using the what?
Set builder notation.
Or using set builder, well, span is also using set builder notation. Like, I mean, here, I have, this. The answer to this progression is t plus 7, t8, 9. Now, this is kind of a bad example because it's not homogeneous. This is not what I want at all. Let me ignore that problem. So set builder notation alone can be just, and this is something you guys were weak on when I tested you. I mean, and it's a traditional source of weakness. Oh, come on. This is what I get for cleaning my office. S plus t, S minus t, S, all right? If I ask you, is this a subspace? You're like, well, you used a W, so it's a subspace. Well, it's not actually an argument. And you could use the subspace test theorem, right? But that does seem rather awful here. You know? There's a much, much simpler way to argue that this is a subspace. Right? You can rewrite it as a what?
Combination of S and T.
Linear combination of S and T.
Oh, of the vectors that, yeah, S and T is a constant.
Yeah, this is the span of what? And what?
One, minus
One, negative 1, 0.
That is a good sign. Now, if you guys can just make that connection when the actual test comes, you'll be in a much better position. Because you won't waste 20 minutes to try to prove this by the, subspace theorem. Much more laborious to prove this by the subspace theorem, right? Yes, Chris?
I was going to say, wasn't that something like the answer to the first question on test 2?
Yeah, something like that. It was, right?
Yeah.
Sorry, I'm keeping track here. Now, that's one way you can describe W. What's the other choice you have for describing W?
There's a direct sum of something?
Oh, that's also something, but I was thinking more in terms of basic principles. I mean, you either have a span, right? Or on the other side of things, you can write it as a solution set to an equation, right? So you can write it as a kernel, basically. This is the kernel of what?
Kernel space is a subspace, right?
Yeah, I mean, W, you can also write W is equal to the kernel of some particular matrix, right? Or null space, rather, yes, thank you. I try to use null space for the matrix, kernel for the linear transformation, okay? So what matrix? I mean, how do you figure out that?
Set it equal to 0 on the side.
Wouldn't it be 1, 1, 1, 1, negative 1, 0?
Would you take like the vector containing S and T multiplied by the basis things, the matrix for those, and then set that equal to 0 and figure out what that is?
Can we just do spanning?
Now he's going to tell us
Oh,
except for
wait.
using spanning
It's
set.
a linear transformation, so like is it
Something
like
is
0 or
down,
something?
Sharon.
First of all, what size matrix should we be looking for?
3-way.
3 by 4.
2 by 3?
3 by 4.
2 by 3.
3 by 2.
2 by 2.
Oh, wait,
W is two-dimensional, right?
Yes.
Spanning is direct. The dimension of a space, a subspace built from spanning is the number of linearly independent vectors in the generating set, right? But how about equations? It's dual to that, right? If I'm in a 5-dimensional context and I give you 2 independent equations, the solution set is 3-dimensional. If I'm in 3 dimensions and I want to describe a 2-dimensional subspace, I just need 1 equation. So I'm actually looking for just a row. It's the null space of the null space of a row vector. Which row vector?
Would it be 0, 0, 1?
Don't think so. I mean, here's the way I would attack it. A lot of classes. I would say this is X, this is Y, this is Z, and I want to eliminate the parameters S and T. That's how I'd look at it from a Calc 3 perspective, right? X is equal to S plus T, y is equal to s minus t, z is equal to s. How do you eliminate the parameters?
X plus y minus 2t.
X plus y. I'm not allowed to use t though.
Minus 2z.
Oh, you said x plus
2z.
x plus y minus 2z equals 0? Indeed. So the row we're looking for was 1, 1 minus 2. Yes.
Actually, we'll probably get to it.
Now, short of adding equations through some sort of intuition, which I can't understand or explain where it comes from for us, right? I mean, personally, I don't really know where it comes from. I think it's innate, part of it. But you see, there's something very unpleasant about what Daniel just did, which was he just thought to add in some certain way to make it happen, right? Is there a more reliable way we can understand what we just did? In terms of some larger theory. Geometrically, what's the relation of that? What's the dot product of this and that?
0.
And the other one?
0.
Coincidence?
Probably
No.
not.
I know.
So it's like
We use gram
It's
Schmidt.
W
the
per.
orthogonal complement.
Yeah. It's connected to the basis for the orthogonal complement. Now, I don't think I've made that explicit in the note, but I don't think this is a calculation we talk much about, but it's kind of important because sometimes you can describe a problem in terms of span, sometimes you can try to describe a problem in terms of equations. It's useful to know how to get between the two worlds, right? So what we're just saying is that if you calculate W perp, right, then that's going to be the span of some vector, let's say V3, right? And you can also write W as the kernel of V3 transpose in this context. That's going to generally be true. So a systematic way to convert the span to an equation, take the vectors in the span, you transpose them, stick them in a matrix, chop, 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 chop. Row reduce that thing, that gives you, that row reduces to something, then you write down the vector solution to the null space, and the generator of the null space, when you transpose them, make those into equations. They give you the equations which describe the original subspace. That would always work. Who cares? I don't know. Anyway, let's see. What else did we learn in test 1? Inverses, right? How to find an inverse of a 2x2 matrix. Properties of inverses like socks, shoes, right? Matrix algebra. What's the main principle of matrix algebra?
Non-commutative.
Non-commutative, right? And other than that, there's induction problems like this, which are fun.
Multiplication definition.
Multiplication definition's a big one, right? I usually test on that in the final somewhere. Problems about symmetric matrices. If you missed problem 7, by now you realize, oh man, I could have got that one, right? I mean, you should feel that way. Because it was, A is symmetric, it's a symmetric matrix. M is equal to I minus 2A. Prove or disprove, M is symmetric. The proof is like, yeah, it's just take the transpose of it. If you get back where you started, it's symmetric. If you don't, it's not. Although if you get minus what you started, it's anti-symmetric, right? So, and what Landon was talking about, problem 8 is a good example of that, right? Anyway, there were elementary matrices, don't forget about those. As I was telling you guys, you don't absolutely have to write the row operations on an arbitrary problem. If I really want you to explicitly denote the row operations on the test, on the question on the final, I will say so. So you're free to use this shorter notation, just that it's row equivalent. But our 2 matrices row equivalent.
We can,
What was the question?
what does it mean for two matrices to be row equivalent? You can get from one to the other by a elementary row operation, of which there are three kinds. What are those three kinds?
Switching rows.
Switching rows,
Adding, subtracting rows.
Multiplying by scalar.
yeah, multiplying a row by a non-zero scalar, and then adding or subtracting rows, right? Of course, we sometimes do both of those at once. Like we do a non-zero scaling of one row, and then we add that to the other. So, I mean, I guess technically that's a composite of the two, but that's usually what we do. Yeah.
And all invertible matrices are row, whatever you said, to the ideal, right?
Well, excuse me, we did talk about a notion of what's called matrix congruence, right? And matrix congruence is a little bit different than what we ended the course with, because matrix congruence allowed us the freedom to change the basis in two different ways, like in basically the domain and the codomain. But if we have A and B are m by n, right? Then we say A is congruent to B, and we proved this if and only if the rank of A is equal to the rank of B, which is actually equivalent to saying that there exists P in, let's see here, oh, I don't know, R something by something, and Q in R something by something. We'll figure it out here momentarily, such that what? Such that B is equal to, I just put P inverse here as a point of making it look similar to the similarity. Oh, sorry about that. It's an unavoidable pun. So P inverse AQ, let's see, to multiply P on that side of A, what size does that square matrix P have to be?
Something
M
like
by
that.
N. M by
M by N, very good, yeah. And the other one has to be
N by N.
N by N, yeah. And what else did we prove? We proved, because you're allowed to use a different matrix on the one side and the other, because P doesn't have to be equal to Q, gives us a lot more flexibility in redefining the basis, essentially. And so what we found was this was true if and only if, you know, if you let L, L of V equals AB, the usual thing, right? Has the matrix of L with respect to some choice of basis, say beta and gamma, equal to the identity matrix, let's say size P, oh, P is bad choice. Anyway, it's the rank of A big, padded with zeros. For some basis, beta for, let's see, where's beta the basis is for, oh, I guess Rn, and gamma for Rm. So matrix congruence is kind of, I mean, it's interesting, but at the same time it's boring, because if you give me two matrices and if you ask me if they're matrix congruent, the answer is yes, if they have the same rank and they're the same size, and that's it. So to classify matrix congruence, I merely need to concern myself with the question of how many linearly independent columns or rows. Now the question of whether A and B are similar is a much more delicate question, because there we're looking at a square matrix, and there we don't allow ourselves to use P and Q be different, right? We have P equals to Q, and so we're looking at P inverse AP, and we've explained in the last 2 weeks of the course or so that A and B are similar only when they have the same Jordan form. Or real Jordan form if you don't want to restrict yourself arbitrarily in the real case. I mean, real Jordan form always exists. The Jordan form for a real matrix doesn't exist when?
In the reals, when you don't have enough eigenvectors.
Right, if I had a complex eigenvalue rather, which would give me a complex eigenvector. We also talked about composition of transformations. Let's see what else here. So basically, the first test is all about row reduction and how to interpret solution sets mostly, right? And some, inverse matrix calculation, the index notation. Those are the big ones. The rank nullity theorem it looms large in the first test material, right? The column correspondence property, you must understand the column correspondence property. I do test on that for sure. Yes?
Speaking about column correspondence, can you do an example where you're trying to find if two things are in the span at the same time?
You just
So, the basic spanning question?
Mm-hmm.
So like, is 1, 2, 3 an element of the span? Say 4, 4, 4, and 0, 2, 2?
Well, like two things at the same time.
Two things at the same time?
Yeah.
Oh. So basically, that's just asking the question. I mean, the simple thing is, I would calculate the reduced echelon form. Let's see here. I put the things that are in the generating set first. And then I put the things that I'm trying to see if they're in the span last. Right? And then I do row reduction.
Mm-hmm.
I'll let you guys work on that. I'm gonna cheat.
Okay.
What? Oh, fine. So mean to me.
You're just trying to see, like, if you do the RREF, then the right one is in the left side and the right one is in the right
Bless
side.
you.
How many rows, how many columns? 4 and 4, right? So,
No, 3 and 4.
3
oh,
rows.
3 and 4. So here, can you guys read it to me?
4,
0, 0, 1. 4, 2, 1, 2. 4, 2, 0, 3.
2, 4. What was that, Sharon? Couldn't hear you over the sound of your shirt.
You're not funny.
She's laughing.
Then why are you laughing?
You made him pause. Chris gets a 0.
Thanks. 1/4. 0, 1, 0, 1. 0, 0. 1 and minus 1. Well, good news. The answer is no. Neither of these are in the span.
And that's because you have 0 equal to 1 and 1 equals 0.
Right, because when you really look at the what does this really mean? I mean, to say it's in the span is to ask the question, for example, is 0, 1, 0 is equal to C1 times 4, 4, 4, right? Plus C2 times 0, 2, 2. So can I solve that equation? Well, that corresponds to, this matrix of coefficients and that inhomogeneous term. And as you can see, it's an inconsistent system, yeah. Okay, so it failed, but can you guys tell me a vector which is in the span? On the basis of this calculation, by the column correspondence property.
E3.
How about this, if I take V3? How about this, if I call this one V3, and if I call this, let me call this one V1, let me call this one V2. What if I look at V1 plus V2? What happens then?
The bottom thing goes to 0, so you're good.
Right? So V1 plus V2 would give me another column over here, which would have been 1, 4, 1, 0. Right?
That's an element. So that is-
By the column correspondence property, what I'm trying to say is if I add, I don't know how to words, but I can see from these two that if I add those, that gives me this column, and then I'm pretty sure then by the column correspondence property that we'll have that V1 plus V2 is equal to 1/4 of V1 plus what? V2? Is that right? Weird. Huh. Is that right?
Yeah. Because it would be 1, 3, 3.
Huh. Let's see, v1 plus v2 is 1, 3, oh yeah, 1, 3, 3.
And then 1/4 would be 1, 1, 1 plus 0, 2, 2. Should be 1, 3, 3.
But what's 1/4 of v1, 1/4? I don't see how that could be true.
Oh wait, no,
Yeah, I think I'm wrong.
no, it's
right.
the 1/4 of the first element in the span
Yeah, it's in this.
plus the second
It's not
element in
the
the
same V1 and
span.
V2.
They're two different
Right, wrote it
V1s.
twice, but it's not the same.
Yeah.
Oh, I'm sorry. I shouldn't say v1. I should call. I need to give these names. I'm an idiot. Let's say
Pac-Man goes.
Sharon 1, Sharon 2.
Yeah. You spelled my name wrong.
Wait, how do you spell your name?
SHARIN.
1, 4.
Okay. Like Sharon is Karen?
Like sharing joy, like I share joy, get
Sharon 1.
I thought you were gonna say something weird like CHERON.
it? Never mind.
So I take 1/4 of Sharon 1 plus. I'm sorry. Let me fix this. 1/4 of Sharon 2. Should it be this? No.
Sharon?
Sharon or no? I mean that's like a share. I don't know. We could find other ways to misspell Sharon, but this will suffice for today. Let's see here. 1/4. Yeah. Is that right? Yeah. Oh, okay. Yes. So I mean, you can take a given row reduction and do some simple things to gain more knowledge from adding columns and thinking about that. Any questions about test 1? Let me move on.
So for this one, we found that, okay, those two are not an element of the span, but then you found something that would be an element of the span.
Right.
Right.
In fact, v1 plus v2 would be in the span because there it is.
Okay.
It's in the span of assurance. Oh, I'm sorry. Okay, so you guys asked me about a Jordan form. No, I mean, I think the best way to answer that kind of question is just to look at an example with some simple data. So suppose you've got a matrix or a linear transformation T such that, well, I guess we could look at this, T of V1 equals to 4V1, and T of V2 is equal to 4V2, or minus 4V2, no, plus 4V2 rather, sorry, plus V1. And we can have T of, let's see here, how about T of V3 equals to, oh, how about T of, T minus 4I at A times V acting on V3 equals to V2, and then finally T of V4 equals to 42 V4. Okay, great. And then I could say find the, if suppose T is acting on a 4-dimensional vector space, what's the Jordan form? This would be enough to figure it out. So given T is mapping from V to V, this is 4-dimensional, and I also need to tell you that V1, V2, V3, V4 linearly independent, right? That's enough, then you could figure out that in fact, what's the Jordan form of T. The reason you could do that, of course, is that you see T minus 4I times V1 is what? 0. And T minus 4I times V2 is equal to V1. You see what that tells me is that T minus 4I times V2 squared is equal to 0, because that's t minus I. I mean, when I multiply this by t minus 4i on both sides, I get t minus 4i on v1, which is 0, so that says that. And then if I look at t minus 4i on v3, I get v2 as it says, so that tells me t minus 4i cubed of v3 is equal to 0. In other words, v1, v2, and v3 is a chain of, it's a 3 chain, or a 3 cycle, if you like, corresponding eigenvalue 4 for t. And then I've got that isolated eigenvector with eigenvalue 42 before. So if I let beta equal to v1, v2, v3, v4, an eigenbasis, a Jordan basis rather, then the matrix of t with respect to beta would be what? 4, 4, 4, 1, 1, 0, 0, 0, 0, and then 42. Zeros elsewhere.
So did you take those equations and put them in Jordan form? Is that what you just did?
I'm supposing that the stuff at the top of the board is given, because sometimes I like to ask a question about Jordan form which doesn't require you to do 3 hours of calculation, you know? And so if this is given, then you can figure out. The point is, you need to recognize that that algebraic data tells you that v1 is an eigenvector, that v2 is a generalized eigenvector of order 2, that v3 is a generalized eigenvector of order 3, and that they're linked, so they form a cycle, a 3 cycle. And then the 42 sits alone, but it's 4-dimensional, so that's it. It's a 4 linearly independent generalized eigenvectors that gives me a Jordan basis. And then this is the standard form associated to that. I mean, if you want me to be specific, the reason I know that, although I don't actually think through this is just a result that I know at this point, but the first matrix would be t, the first column would be t and v1 in the beta coordinate system, right? So like, what is t of v1? Well, t of v1 is 4v1, right? What is 4v1 in the beta coordinate system?
4, 0, 0, 0.
Right, that's 4, 0, 0, 0, right? Because why? Because v1 is the first thing in the basis, right? Now I've got 4 times the first thing in the basis. That means the coordinate vector is 4, 0, 0, 0. Let's look at a question from test 2 before I run out of time here, which is soon. Let's say we'll go until 12:40, okay? I don't want to keep you guys too long.
Stay here all day?
Stay here all day?
Oh,
Go over everything again.
Okay.
Just reteach the entire
LOL.
class.
The entire class. Yeah, right here.
Let's have movie day.
So anyway,
Yeah.
there are questions you can think, and I'm not going to answer this, but you can think about questions like, how would you find the basis, for example, of, well, I will say, but I want to work an example because that'll take too long. But here's something you can think about. Suppose you have 2 subspaces, W1 and W2, right? There are 2 natural subspaces you can form from W1 and W2. So suppose you got W1 and W2. Oh, why did I clean my office? Why did I do that?
Did you put them back on the
Table ones, if you know that they don't work.
It's too late.
Then you don't pick them up again.
I know. So W1 and W2 subspaces of some vector space V. Then what?
All of them are fine.
Then what? What are 2 natural subspaces you could form from these 2? Yeah?
The perp subspace?
Forget about perp for a second here. No perp.
No perp, okay.
Yeah.
They're union and intersection.
Union would not be a subspace though. I agree with intersection. So W1 intersect W2 definitely would be an example of a subspace. Often I ask for proof of that. Can you prove that's a subspace?
Yes, you can.
Yes, you can. You just that would be a good place to use the subspace theorem, right? Pick an element pick x and y in the intersection, right? Show that x plus cy is again in the intersection.
That was the
And
test question, right?
to do that, you just know that like, because there's an intersection in both of them, so you can just kind of go from there.
Yeah, that's a good, that was a test question, is a good comment. This last comment says question. Where's my test two? What are you saying, Landon?
And prove that you like note that like since they're subspaces, the zero has to be, like you just know because the things are in both of them, they're like, because like since they're subspaces, zero has to be in both of them, so that's an intersection.
Right, it's not empty because not empty because zero's in there, that's right. Oh, and yes, Chris, you were right. The first problem on test 2 was exactly that span question. Yep. I almost always ask one of these linearly independent questions, and so what was the cardinal sin on test 2 for this problem? I'm getting distracted from my stated goal, but you guys assume they're column vectors, but they're not column vectors, they're abstract vectors. You can only add them and multiply by scalars and use basic logic to do this problem, right? You can't put them in a matrix and row reduce. That doesn't make sense. Okay, or at the minimum, you have to explain where that system of equations you're looking at came from. Excuse me. What was I looking for here?
W or
Was-
something.
Maybe that, was that in the
I think
quiz?
It was a quiz.
It was a quiz.
Yes.
That was the question,
Question
the
15.
dreaded question that made you fail like everybody in the fall of 2013.
I didn't fail them, they just,
Dang, pass.
It was question 15
most people passed.
on quiz 2.
Happened not to give an A that semester.
At all?
No. Hey, it's the only time it's ever happened for me.
What?
It's the only time that's ever happened in my courses with more than one person.
Question 15 of the quiz, is that what you said?
Quiz 2, question 15. It isn't hard.
Oh yeah, there it is. So,
It's just, it actually requires you to know like the properties of a subspace a little bit.
How do you know about fall 2013?
He told me.
Oh.
I pay attention to things like that.
It's
I
really
think I
slow.
I
posted
kind of know
this.
everybody's grades in this class.
I posted.
means mine, and maybe Daniel's.
Well,
I-
Daniel's
about it.
Daniel's got like perfect scores on everything. so
Didn't I
that was
post a
easy.
didn't I post a solution to quiz 2?
I
Yes,
hope so.
I have it, if you need it.
No. I can't find mine. Oh well, let me get back on track here. So yes, that's a subspace, but there's another thing. Not union isn't subspace, but what is?
Union and intersection?
Direct sum.
Well, it doesn't have to be direct though. I don't need. I mean,
Just.
yes, just some though. So, you guys know what W1 intersect W2. That's set theory, right? W1 plus W2. What's that defined to be? That's just x plus y, such that x is W1, y is W2, right? You can prove that that's a subspace as well, right? Again, that's a good candidate for subspace test question. But then, here's a question. How do you find the basis for these? From the basis, say, suppose you know a basis for W1 and W2. How would you find the basis for these?
For W1 plus W2?
For W1 plus W2, I know what to do. It's what Daniel said. What is it?
You union them.
Union them, right? The union, although you might have to remove some linear
Like
dependence.
intersection and union, kind of, right?
But isn't the union
Or
without
not
intersection, without dependency, the direct sum?
Yes, this, sometimes you can put a circle around the plus if the W1 intersect W2 is 0.
Yes.
But the question though is, okay, so great, yeah, you're right. To find the basis for W1 plus W2, you just union the basis for W1, the basis for W2, and then if there's linear dependencies, remove them, as we know we can from the plus minus theorem. The intersection though, it's tricky from the viewpoint of spanning. But here's a thought for you. If you knew that W1 was the kernel of T1, and if you knew that W2 was the kernel of T2, maybe you could figure out a characterization of the intersection in terms of those T1s and T2s. Let me make it more simple. In Rn, yeah.
Isn't it kind of like they're like the perpendicular thing again? Because like one's the null space of the other, so they're kind of like opposite. So they kind of maybe it's that.
Well, I haven't said anything about orthogonality here or perp. I mean, I'm not assuming that. W1 and W2 could be something like this line and this line, right?
Yeah.
And if you look at what's the intersection, so I mean, what's the basis here? The basis could be vector 1 and vector 2, right? And if you look at the intersection of V1 and V2, it's certainly not a basis, it's the empty set. So certainly the intersection of the basis need not be the basis. Well, here the intersection is 0, so this is a bad example, sorry. That's not the example I want. See here. Curses. I needed a two-dimensional example. Sorry, guys. Oh, I said I wasn't going to get into this far. Anyway, the point is it's not terribly easy to figure out the span, the basis for the intersection from a spanning perspective, but if you look at it from an equations perspective, it's not that hard. For example, if I ask you how to characterize, if I have two subspaces in Rn, one is defined by set of equations 1, the other one's defined by set of equations 2. What would the intersection of those subspaces be defined by in terms of equations?
The things that solve both the equations.
Exactly. You just take the equations and you slap them together. So to describe intersections from from initial data, it's much easier to combine equations than it is to combine spans. The spans are not just simply combined. In fact, it could be that the intersection has neither of the bases in it. That's possible. Not even taking the basis and removing things. Because what can be in the intersection is sums of bases. Anyway, I'm digressing. So, what do we want to talk about? What was I about to talk about? Oh, coordinates. You guys always forget about coordinates at some point or another. How do you... So how do we define coordinates?
Like v sub beta.
Right. Let's look at an example of exactly v sub beta, or what, or phi of beta if I use that other notation, right?
He erased you.
What's that?
You erased Sharon.
Oh.
It's probably for the best.
You weren't supposed to erase her until Friday.
T.
Nah, man, you might see me.
Let's suppose T of A, B, C, D is equal to A plus B x squared plus CX plus D minus A. There we go. So I can ask, what's the matrix of T with respect to, let's say T beta gamma, where what? Where T is a mapping from, let's say, R2, 2 by 2, to polynomials of order what? Apparently 2, right? Over R, if we use the notation in D'Amato and Little. And then I need to tell us what's the basis going to be. So here, we'll use basis beta equal to what? Well, the standard thing to do, I usually do 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That's my go-to, unless somebody says otherwise. But I'm going to let us choose gamma such that T beta gamma is equal to the identity matrix padded with zeros. So I'm going to give us freedom over the choice of gamma. This problem's not quite mechanical, right? Because I gave you a choice. you have to think. So what does it mean? What do we know? The theory tells us that this identity matrix, what's the size of the identity matrix?
The rank.
The rank. What's the rank of T? It's the dimension
Of the column space.
The column spaces make sense here. It's the dimension of the range, right? We're in the abstract context.
So
Rank nullity still applies. So rank plus nullity is the dimension of the domain. What's the dimension of the domain here? 4, right? So we have 4 is equal to the rank of T plus the nullity of T. I think nullity of T is the easiest thing to calculate, because there we just have to understand what's in the kernel of T. What's in the kernel of T? That's just A such that T of A is equal to 0, right? It's the 2 by 2 matrices which map to 0. So what would that be? A, B, C, D, such that A plus B, x squared, plus CX plus D minus A is equal to 0. So what? I've got no black markers in here at all. I'll be right back. You guys calculate that. Find the basis for the kernel while I'm walking.
we're not. Jokes. Rank is 3. Because it's a P2, it has to be right.
Not necessarily, like just looking at it.
What happened? Let's see here. I see from this, A plus B equals to 0, C is equal to 0, D minus A is equal to 0. C equal to 0, that's easy to understand. This says that A is equal to D. Also nice. Oh, this says that B is equal to minus A. I say we look at A as the parameter. So D is equal to A, B is equal to minus A, C is equal to 0. So in fact, this is equal to matrices of the form A minus A, 0, A, such that A is a real number. Or if you like, it's the span of 1, minus 1, 0, 1. So now we know what those zeros are. How many zeros are there padding with T?
1.
Yeah, just one column of zeros.
So that means that your domain is 1, and your rank is 3, or your range.
My nullity is 1.
Your nullity is 1, and your rank is 3.
Right.
And that corresponds to the range. But couldn't you have known that your rank was 3 because it's a P2, it's a second degree polynomial?
Well,
Or is that?
I'm not sure that it fills out the whole P2 until I look at the equations. I mean,
'Cause it
yeah,
could've,
this
like-
is simple enough. You could have seen that you get an arbitrary arbitrary quadratic from my formula. But short of seeing that, no. Because, just because I'm going into P2 doesn't mean I'm covering all of it.
Okay, so like maybe like if, well,
So what I'm trying to say is picture something like this. Here's V, here's your linear transformation T, here's W, right? Some subspace of W is the range of T. It doesn't have to be all of W. So the fact that W is 3-dimensional doesn't tell me that the rank is 3-dimensional. There's a distinction between the codomain and the image. You call this image. Right? More specifically, it's T of R 2 by 2. So theoretically, that's what it is. Okay, so, all right, well, then what? Oh, I've set us up for the fall because I can't use beta like I do. I can't use that beta. That won't allow me to do what I want. Right? Because I need the fourth element of my basis to be 0, to map to 0, right? So I need to redefine beta. Sorry, I have to take this away. No sharing. Choose beta and gamma. Choose gamma and beta, such that that. Oh man, now we have so much freedom, I don't even know what to do. But this much we know, we should choose beta equals to something, something, something. The fourth thing, I want to make that 1 minus 1, 0, 1. Because I know that will do what? What's the matrix of T look like? Remember, we're matrix of T, right? Beta gamma. It's the first thing is T of V1 in the gamma basis, and then you have T of V2 in the gamma coordinate system, T of V3 in the gamma coordinate system, T of V4. And T of V4, I'm saying I want to be 1 minus 1, 0, 1, because I know that that makes this be 0, which makes the whole fourth column be 0, right? So that choice is clear. Now what should I choose? Yes?
So we just need 3 linearly independent vectors for beta.
Exactly.
That are not dependent upon the last.
Right, and that is exactly why this problem, as it's currently stated, is a misery to grade. Because there are infinitely many choices for the first 3 things you could put in beta.
So you could do like 0, 0, 1, 0,
You said 1, 0, 0,
or 0, 0, 1, 0.
0, 0, 1, 0? Okay.
That works too.
Just like 0, 1, 0, 0.
That would be my choice. Now, are you sure that those 3 are linearly independent from the fourth one? I'm not.
Yeah, because none of them have the
The
1 at the bottom, right?
Oh, okay, I got you. Right, Daniel's right. I mean, that's a good way to see it. So if you focus on the 2-2 column, 2-2 element, see this? There's no way you can take those zeros and build this one. So it's clear that that is not linearly dependent on the first two. My mistake was thinking about the other 3 components and not that one. I hadn't got to it yet. But then you guys got ahead.
So why does that one have to go to 0?
Which-
The last one? Why does that go to 0?
The point is I need a linearly independent set for the basis. So how can you be sure that something's linearly independent without doing a bunch of calculations?
Does that go to 0?
You can just look for something that's a characteristic of one vector that can't possibly be built from the others.
Mm-hmm.
That's, because you don't really want to do the calculation if you can help it, right? So there you go. Then what do I choose for gamma?
You need to do the
2 better.
I need this to be what? I need this to be, we need some notation here. So this guy, guys, this is V1, this is V2, this is V3, this is V4, okay? And then we need to figure out what gamma is. I'm saying gamma should be, what is it, G1, G2, G3, let's say. Okay. So my suggestion is just this. Whatever T of V1 is, call that G1. Whatever T of V2 is, call that G2. Whatever T of V3 is, call that G3. And that makes the magic happen. So what is G1?
it's just ax squared minus a.
So it's T of 1, 0, 0, 0. And what was that?
X squared minus 1.
It's x squared minus 1? Okay. You see the coordinate vector of x squared minus 1 with respect to gamma is equal to 1, 0, 0 if gamma is equal to, x squared minus 1 comma stuff. Right? That's the way it works. That's the definition of the coordinate vector. Well, what is the definition of the coordinate vector? I mean, I was trying to get back to that at the start of all this. I don't think I ever actually said it. That's something you should know, right? I keep using it. I haven't stated it. Yes, then?
I mean, the definition, it's like v sub beta is equal to the, it's, all right, so you have like the summation, k, or I equals 1 to n is equal to x sub I, v sub I, where v sub I, like v sub 1 to v sub n is, in the elements of the basis, v sub beta is going to be the x1, x2 to xn.
I agree. So what you're saying is this, if and only if the coordinate vector, which we also denoted this, right,
Yes.
is the column vector. So that's the definition of the coordinate vector, coordinate mapping. But of course, as we actually use it, what do? So often we just use this, that the coordinate vector of the j thing in the basis is just ej, right? Operationally, often that's what I'm actually thinking about. That's what I did here. See, this is the first abstract basis element in gamma, so it spits out E1. So, anyway, there's a slightly non-trivial example of finding a matrix for a linear transformation. Now, usually, oftentimes I give you the basis beta and gamma and just ask you to find the matrix, right? But I can also give you freedom if I want to be challenging. Right?
We don't have freedom.
You don't like freedom? Freedom is, that's right, this is just liberty. But you want liberty, just no freedom? Okay. At liberty, there can be no freedom. It doesn't seem right somehow. I don't know. What's the difference between liberty and freedom?
Liberty is a school.
Liberty's a school?
Freedom is also a school.
Freedom's also a school, yeah, probably.
School of that.
High school in Miami.
Somebody should start an actual Hudson University in New York City.
Hudson University.
Hudson University is this like fictional university that appears across a wide spectrum of fictional crime dramas. Like Law and Order will refer to it. We were watching Castle, I think, the other
Wait,
day.
so they refer to a fake place?
Yeah, there is no such thing as Hudson University, but it's kind of a pseudo Columbia that they've made up for the purposes of impugning it. They want to impugn an arbitrary school with whatever scandal, right? But they don't actually want to make the story about, you know, the
Columbia, Liberty, Harvard.
yeah, whatever.
I
Exactly.
just put those in the same.
Yeah.
Is it prestigious?
Well, there's Harvard Street over there.
Oh, yeah,
I
there
mean, you've
is.
seen it. Anyway, guys, obviously I can't cover the whole course in an hour and a half or whatever, but review the tests, make sure you know the definitions, should be
Okay.
fine. Make sure eigenvectors are so important. I often ask simple questions about eigenvectors. You know, there will be something computational, right? But I would be very surprised if I'm not going to ask you about the deep inner workings of finding the Jordan basis. That's not something I've assigned homework on, and it's really involved, as you can see from reading chapter 6 if you have. So I'm not going to test on that because it's not fair to, because you haven't done it. And even if you were to do it, you ought to do it with MATLAB or something. It's really not appropriate for an in-class test. But the thing I showed you up here, where I give you data and ask you to find the Jordan form, that's completely within bounds because that just it requires you to understand the relation between the basis and the transformation and what the Jordan form looks like, right? Make sure you know those tableaus. That idea is helpful. Anyway, the Jordan form, all of that discussion, you know, altogether is maybe 10% of the final. Most of it is about column correspondence property, the basic, you know, matrix algebra we did at the start, subspaces, linear transformations, prove something linear transformation. Don't forget you need to know how to do that, right? All those things. And of course I will ask a question about isomorphism. That should be there somewhere. Yes, sir.
And know how to prove the coefficient equating property.
Dr. Ma'am, test questions.
I mean, it's easy if you know it.
Everything's easy if you know it.
It's like the coefficient equating property.
Oh, the equivalence of equating coefficients and
Yes.
linear dependence.
Wait, the proof of why you can equate coefficients?
Will that be on the test? Because I like that proof. I got it right.
Yeah, they're trying to talk me into a question, I see.
I mean, I just wondered one thing was on the test.
You can't be so direct about that. Like the approach you need to take with a professor, you have to say, that won't be on the test, right? Because you wouldn't test on that. But you got to lay that gauntlet down earlier in the semester. You can't do it now. It's too transparent at this point. You need to plan ahead. All right, that's something you should have put into motion weeks and weeks ago.
Man, I really hope that Dr. Cote doesn't make us calculate the RREF of a 2x2 matrix.
I don't know if I can do it.
I once did
And
this.
make it worth
I think I
50%.
told you guys. I think I
You
told.
said,
I think I've told you guys before, but I did this in my mechanics course. I went to the professor like 2 weeks into the course. It wasn't my intention to make anything happen in particular. I just was generically speaking annoyed that we were never tested on theorems. We're always tested on problems, but we do prove certain theorems in general mechanics, and I thought, like, I want to study for those. I like those. They're interesting. So I said, that won't be on the test. And he's like, well, why? I was like, well, we don't have to prove theorems on tests. And I just stated it like categorically. It wasn't on the test.
you didn't make any friends.
But it was on the final. The whole class was like, what was that question? I was like, that was my question.
And then you never made any friends.
Did you get it right?
Yes.
Did anybody else get it right?
Crazy Paul. He practiced it dozens of times.
Was he
It's
one
the
of
reason he
your
passed
friends?
mechanics. What's that?
I said, was he one of your friends in the class?
Yes, he was one of several friends I had.
Uh-huh. Imaginary don't count.
Actual reason for the question.
Yeah.
For our number theory test on Monday, you won't ask about simple congruence modular questions. I would be crazy, right?